A 2-second delay changed how we map the universe. Here's the punchline: tiny timing quirks can flip big stories. Subtle signals are faint patterns hiding just above noise. They matter because missing them erases real physics from our notes. Astronomers learn to tease whispers from static, then verify ruthlessly. These are the cosmic whispers that almost slipped away. Midnight at a mountaintop observatory, the room hums like rain. A screen shows snow, but a thin line repeats stubbornly. That line is a subtle signal begging not to be ignored. A subtle signal is a repeatable pattern barely above noise. You should care because physics hides in those near-vanishing quirks. Ignore them, and entire chapters of the universe remain blank. The hunt starts with calibration, which removes bias from instruments. Then detrending subtracts slow drifts, leaving quicker changes behind. Next comes stacking, where many weak traces reinforce each other. Finally, cross-correlation checks whether two datasets hum in sync. Matched filtering pushes deeper, comparing data to predicted templates. Rule of thumb: real signals repeat across setups and frequencies. Here is a concrete case you can picture right now. The cosmic microwave background is a glow from the hot Big Bang. Its temperature is about 2.725 Kelvin, almost perfectly uniform, but it has ripples only 1 part in 100,000. Those ripples looked like static until careful maps revealed waves. Tiny differences sketched sound patterns from the early plasma. The first detections looked fragile, almost too neat to trust. Teams confirmed them with different satellites, seasons, and scan paths. Numbers tightened and peaks lined up at precise angular scales. Bottom line, the smallest reliable bumps can carry the biggest truth. Far out in the radio quiet, dishes stare at pinpoint beacons. Each beacon is a millisecond pulsar, a cosmic metronome in space. A pulsar timing array is a galaxy-sized detector for slow waves. It matters because those waves come from giant black hole pairs. Supermassive binaries tug spacetime, stretching and squeezing over years. Their signal is tiny, but it nudges pulse arrival times. Astronomers time pulses to microseconds, then compare thousands of ticks. They subtract clock errors, ionosphere wiggles, and observatory quirks. What remains are timing residuals, the leftover early or late blips. If residuals correlate by sky angle, the curve should arc. That arc is the Hellings Downs pattern, a geometric fingerprint. In 2023, teams saw a common hum across many pulsars. The hum's amplitude matched a background with strain near 10 to the minus 15. Pairs of pulsars separated by 60 degrees shared stronger agreement. Further apart, the match relaxed, exactly as the theory predicted. Tiny tests scramble sky positions and the arc disappears completely. Keep the real geometry and the arc stubbornly returns, sharper. One array tracked about 200 pulsars for 15 years. Another added southern dishes, extending baselines and pushing precision. Results converged, and the hum solidified into a new background. This background maps a hidden census of merging black hole giants. So the picture is, clocks across the sky confirmed a faint wave. In a quiet control room, a spike flashes for 2 milliseconds. It looks like interference, the kind a microwave oven spits. A fast radio burst is a short radio flash from far away. You care because these flashes weigh the thin gas between galaxies. They race across space and lower frequencies lag behind. That lag follows a clean formula, set by electron columns. Astronomers call it dispersion measure, a count of free electrons. Terrestrial noise does not follow that curve, so it betrays itself. Pipelines clean the data, then sweep templates across frequencies. A real burst lines up diagonally, brightening when dedispersed. At parks, early false bursts mimicked signals during lunch breaks. Those imposters came from local gear, not the deep sky. The first real catch had a dispersion far beyond our galaxy. Duration was a few milliseconds, with energy like a supernova slice. Repeating bursts sealed the case, firing from the same dwarf galaxy. One famous repeater showed a dispersion near 558. Bursts marched across 300 megahertz in tens of milliseconds. Rule of thumb: real bursts sweep smoothly and repeat their curve. Now arrays net dozens per day, mapping matter with precision. Net result: a messy noise problem turned into a new cosmic yardstick. A faint ripple chirped through LIGO, rising in pitch, then stopping. Seconds later, a space telescope pinged with a soft gamma squeak. Multimessenger astronomy means catching the same event in different messengers. It matters because combining messengers multiplies what we can learn. Gravitational waves give distances, while light tells us where to look. two neutron stars spiraled together, shaking space like drumheads. Their merger sent out a wave, then lit a short burst. The burst arrived 1.7 seconds after the final chirp. That tiny delay set tight limits on gravity's speed in vacuum. It also hinted at how jets punch through shrouding debris. Observers swung telescopes and found a new point in NGC 4993. Distance was about 40 megaparsecs, roughly 130 million light-years. The optical glow reddened over days as heavy elements formed. Spectra showed features of newly minted R-process gold and platinum. Radio afterglow rose slowly, suggesting an off-axis jet geometry. Tiny tests shift the burst earlier and models break badly. Shift later and kilonova heating cannot match the light curve. With the distance from waves, astronomers estimated the Hubble constant. One event gave a value consistent with other cosmic yardsticks. More events will refine it, painting a sharper expansion story. Bottom line, 1.7 seconds rewired an entire playbook. On a citizen science website, a green smear sat near a galaxy. It looked like a glitch, weird color, wrong place, no symmetry. A light echo is gas glowing from a lighthouse that just dimmed. You care because echoes reveal flickers in black hole feeding cycles. The cloud was rich in oxygen, ionized by a once blazing core. When the black hole faded, the cloud kept shining for a while. Photons launched earlier still streamed outward, charging the remote gas. Spectra carried strong oxygen lines, but starlight could not explain them. Imaging showed tidal streams, hints of recent interaction or minor merger. Radio maps revealed a faint outflow, nudging the cloud's outer edge. The lag acts like a clock, telling when the core went quiet. Numbers suggested tens of thousands of years since the lighthouse dimmed. The distance from the core was roughly 70,000 light-years. Surface brightness was tiny, the kind that algorithms often drop. A volunteer flagged it, and astronomers pulled every lever they had. Follow-up confirmed a quasar passed, then a sudden recent downturn. Rule of thumb, if gas glows green, look for hard photons. Similar echoes turned up elsewhere, proving quasar flicker is common. What to remember, one odd smear redrew how active galaxies behave. Citizen science saved it, because humans still catch patterns algorithms miss. Once seen, faint cousins emerged in archival images across surveys. Together they timed black hole flickers like a cosmic heartbeat. A small point streaked across images, moving faster than local rocks. The orbit was hyperbolic, so it was not from our system. An interstellar visitor is a body passing by from another star. You care because visitors carry chemistry lessons from alien nurseries. Photometry flickered as it tumbled, suggesting a very elongated shape. The color looked reddish, a sun-baked surface with complex organics. Astrometry revealed a tiny push, not explained by gravity alone. Non-gravitational acceleration can come from gas jets or radiation pressure. No coma appeared in deep images, which complicated the story. But a little outgassing from hidden ices could still fit. Alternatively, sunlight pressure on a low-density body could nudge it. Either way, the push was only a few millionths of gravity. Numbers landed near 5 times 10 to the minus 6 meters per second squared. Brightness swung by a factor of about 10 over a rotation. That swing implied a length several times larger than its width. Telescopes caught it for weeks, then it faded into star fields. Rule of thumb, when paths bend oddly, search for subtle extra forces. Soon after, another interstellar comet arrived with an obvious tail. That one behaved normally, confirming visitors can span a wide range. What to remember, tiny tugs can rewrite origin stories for strange objects. A star's light dips by less than 0.1%. That blip repeats on schedule like a train sliding past signals. A transit is a planet crossing its star, dimming it slightly. You care because tiny dips reveal sizes, orbits, even atmospheres. Space telescopes watch thousands of stars, recording brightness every few minutes. Pipelines flatten trends, then search for repeating boxy shapes. Noise from spots, flares, and pointing jitter gets modeled away carefully. A real planet returns with the same depth and crisp edges, but clocks can slip, and slip tells a deeper story. Transit timing variations happen when planets tug each other gravitationally. Those tugs shift the schedule by minutes, sometimes more. Fitting those shifts reveals extra planets that never transit. Kepler saw swings of several minutes in a compact system. Masses and orbits emerged from timing alone, without direct images. Spectra during transit add chemistry, tasting atmospheres in narrow bands. Tiny test, inject fake dips, and the search should find them. Too many misses means the pipeline is eating real planets. Ground telescopes then refine ephemerides, extending timing baselines. Rule of thumb, consistent depth plus consistent clocks beats any single dip. So the takeaway is, minuscule shadows and schedule slips reveal hidden worlds. These stories started as blips, smudges, and off-by-seconds quirks. We defined subtle signals as patterns barely above noise. They mattered because they carried clues about gravity, matter, and time. We watched clocks across the sky hum with a shared rhythm. We caught radio needles that weighed the fog between galaxies. We timed a 2-second offset that reshaped entire playbooks. We chased green echoes to mark a quasar's fading heartbeat. We measured tiny tugs from a visitor between the stars. We read minute shadows to reveal worlds we cannot see. Rule of thumb, small but repeatable beats loud and untrustworthy. So the picture is, attention plus patience turns noise into knowledge. If this quiet detective work clicked, subscribe to keep the whispers coming. Thanks for listening, and keep your eyes tuned for the faintest lines.